Thanks, Rajat. So folks, now we go deeper into the evolution of how we built this system. It was not a simple start. We wanted to establish some design principles and then go one by one on how we grew these systems. The first things first, we focused on iterative development. Plan sufficient to plan more. Too long a planning is difficult and it's very inaccurate. You won't be able to get it right. The next one was we focused on event-driven architecture. We found that most of our systems did not need real-time request and response. So we pre-computed more and more of data to get it cached into the systems so that the online compute was lesser and lesser. Third, we did not want to box our business into a box. We had to scale horizontally. As the business grew, we did not want to overemphasize and over-optimize within a host. We should be able to throw hardware at things, and that should scale horizontally. Next, we focused on the majority of the benefits. Do not make perfect the enemy of good. And lastly, we stuck to the Amazon leadership principles. We continued to invent and simplify and deliver results as we went about. Now let's go deeper into our campaign management system. This is the system which is there to store the advertiser's intent, what they wanted to do. The other responsibility of this system was also to vend out the updates to these campaigns to other advertising systems where the pre-compute data would be available. We started very simple. There was a simple Java service. It wrote the data into RDS, a Postgres database. We polled into the Postgres database for every 30 seconds, wrote the data into a file journal through which everybody else was reading and streaming the data out. We soon realized that for larger advertisers, Postgres was going slow. We were not able to keep up with it. We went in to shard the data based on an advertiser ID. Some of the data would go into one shard. Based on the other advertiser ID, it would go into the other shard. The polling got a little more complicated, but being naive, we were loving the complexity. We were having fun with building this complicated system. Complexity continued to grow. Business continued to grow. We had more and more shards, more and more loads. The downtimes were increasing. And with every time we had to reshard, there was a minor outage. There was an operator sitting there whose heart would be bumping, thumping. Oh my God, what's going to happen? I did not like that. That's not a developer experience that I would go for my systems. This was the first overhaul of the systems. What we realized was we were building a system which needed automatic partitioning, which needed automatic scaling. And DynamoDB seems to suit the bill. However, there were challenges. The relational data model was to be converted into an NoSQL data model. The next one was SQL queries for joins and where clauses could be written much easily. You can't do that on DynamoDB. So we augmented our DynamoDB with Elasticsearch. To make the data congruent between these two systems, we hooked onto the DynamoDB streams, put them onto a Kafka, streamed it to the other clients, as well as one of our own clients, which would start writing to Elasticsearch. I specifically chose the word congruent, not consistent, because now I have two data stores. Making sure that as soon as the data is written, I can't read it from the other system. There were delays in here, and this deteriorated our performance. What was a strongly consistent system is no more a strongly consistent system. Okay, how do we get the data fast into Elasticsearch? We started writing directly from our Java application to the Elasticsearch. Okay, my P99 latencies came down from about 3 seconds to 1 second, but my P100s, where the fast path would fail, are still coming via DynamoDB, DynamoDB streams, Kafka. This is taking about 30 seconds. That's not good. It's still not raising the bar. Had to innovate more. We continued to dive deeper, went in, what is going on there? Could not get answers. And some genius told us, please upgrade, you are using an older version of Elasticsearch. We upgraded 10 plus versions, and our latencies came down to less than 250 milliseconds. And that was something that we loved. Yay. There was a lot of success available throughout. By the time we got to today's world, we are processing thousands of events. Our availability is more than 99.9. We are truly horizontally scalable. The events are coming to our partners within about 2 to 3 seconds, which was originally where we started from was 30 seconds. To make the data closely available in all the regions, we also employ DynamoDB Global Table Share. The other fun part with this async propagation over DynamoDB Global Tables was that we can now employ other data processings, maybe localizations, if you want to localize the data in particular regions outside of the core main region. So that was the success with my campaign management systems. Storing the data was one part of it, streaming it was another, and now processing it in this real-time request response system, the ad server, was yet another challenge. This system would source all the data, process the ads in real time, and finally select the set few which need to be shown to the shopper. Historically, this system was built to be optimized, and everything was put into a single host. The myth was, if you go over the network, you will incur latencies. And when we are processing a lot of data, every millisecond counted. It was not easy to break that myth. We had about 300 gigs of search index of the whole of the campaign management on the host. We had 150 gigs of the machine learning components, machine learning models, data models, et cetera, on the host. And we had about 300 gigs of caches sitting on the host, which would decorate my ad campaigns to add more data, which would help our machine learning systems eventually. Back in 2018, we were processing somewhere about 1.6 million ads per second. And for each request, we were sourcing somewhere about 400 ads. For all of these ads, we had to for all of these requests, we had to process within a 120 millisecond budget. I'll continue on, but this budget will not change. We will continue with the scale. This 120 milliseconds will not go anywhere else. As the tenets of improving the system, we said that we want to go distributed, service-oriented architecture. What we were eyeing for, that each individual component should be able to innovate independently. We should not be boxed in a box. The next up was we wanted to pre-compute a lot. We did not want more and more to happen real time. You got the data, you compute it, give it to the ad server in a pre-computed manner so that it uses it and moves on. Don't waste time there. It's precious. The third was we wanted to be horizontally scalable. If there is more data needed, we can't shove more in a single host. It will cap out at some point in time. And the business would always want more. There will never be a business which wants less. And the last was transparency. We needed transparency. Over time, what had happened was to optimize this single machine processing a lot of data, people had skipped even logging what was going on in the system. So it was very opaque now. We did not know what is going on in the system. Yeah, we were making money from the business, but was that what we could achieve, or was that what we could achieve? We did not know that. To start with, on going distributed, we first eyed upon the major components. Sourcing was already taking somewhere about 60 milliseconds, and machine learning was already taking somewhere about 30 milliseconds. If we went over the network, probably we will add 2 to 3 milliseconds. We could chew this up for at least these components. The big learning, however, was we went over the network and we gained on latencies. Wow. What had happened again over time, because we were boxed in that box, was the CPU had clogged up. And now that we were not doing so much on that host, the compute became faster. And we were now able to leverage that. The overall X's and Y's played so well that the network increments were lesser than the savings that we did on the ad server. Now the problem left with our systems were to move these caches out. This was a challenge because these were still larger components. Caches would take about 2 to 3 milliseconds to read. Getting them over the network was tough. More so, we had some in-memory files also sitting out there, which would give me the data in 200 microseconds. How would I take them over the network? The journey of improving the sourcing and the machine learning systems went its own way. They used purpose-specific hardware. Machine learning components will be talked by my colleague Kuhn later in this conversation. Let's focus more into how we built the caching solutions at scale. Again, we started simple. There was a Java client. We made it talk to a Redis cache and thought everything should work fine. Our largest cache was reading about 5 keys per add, which meant that we were needing to read the data at about 6 million keys per second. What we realized was that at P99, the latencies were up to 14 milliseconds for this cache. That would not fly. The business would not allow this. We did not have that much time. Okay, we changed the Redis to Elasticache Memcached. That somehow worked. The latencies were flat. This was also the solution that we were using on host. So it worked at least. But we did not get any data replication now. So if there is a data loss and even 1% of the data goes away, that means a burst traffic of 60,000 TPS going to the data custodian systems. It will surely brown it out. We can't build systems which can take this much of burst traffic. Okay, more innovation was needed. We said, why not create multiple replicas of the Memcached itself? So we created a campaign management service which started writing the data into multiple replicas of the cache management systems. The Java client also became a little smarter. It would randomly pick any 2 of those replicas, pull the data in, and just in case if the data was not available in one of the replicas, the other replica at least would serve the request, and the ad server will continue to work fine. The business would continue to work fine. We achieved higher availability clearly with this. But the data recovery was still not there. What happens to the data that was lost? We had to somehow fix that. We added more optimizations into the Java client. And to note, like, these are the places where we had to do innovation, right? There was no simple way that we were able to just upgrade as we were able to do it earlier. This one was going a little more complicated. So now my Java client would basically read these 2 data elements, compare whether both of them are same. If they are not, then the key was published to a reconciliation loop. This was the eureka moment where we did not have to go to our data custodian systems. I have so many replicas, just pick the data from there and put it back into the caches. So these keys that were consumed by my campaign management service. It would go query each of the replicas out there, establish a quorum, establish what is the right data to be available into my caches, and shove it back down. In the edge case that it was not able to establish a quorum, sure, it would go back to our data custodian systems and provide the right data out there. But only the keys that were being read will be backfilled by this manner. Not all the data will be backfilled by this manner. For this, what we saw practically was that caches are pretty highly available. They don't go down so often so easily. And what we focused on was, rather than having all the data in the caches, focus on the hit rate that will be there in the caches. So if the data is being read, that will be reconciled and that will be made available automatically. Your business will not be impacted by this. However, to play safe, we built dynamic configurations and we separated which are the caches that we are reading from, which are the cache replicas that we are reading from, and which are the cache replicas on which we are doing reconciliations. We still built a solution for the doomsday when, say, suppose all the caches just go away. We started to back up our data on S3s and DynamoDBs, but luckily, we've never had to exercise that till date. It's been about 2 years that this has been running. To simplify the data ingestion into our systems, the Cache Manager service was also built and grown and augmented with ingestions from micro S3 files or Kinesis and SNS SQS topics. A fun learning throughout this journey was that at this throughput, the number of objects that are being created itself caused a lot of Java garbage. And the JVM pauses itself were slowing our systems down. But again, here, at least the world came back again for my help. JDK 15 launched ZGC, and we got 98% of improvements for our GC pauses. That, again, calmed my life down a little bit. A myth that we broke was we focused on improving our object creation itself, garbage creation itself, and we started to pool these teeny tiny objects as well from against the standards of you should pool only large objects. At this massive throughput, at this massive scale, if you start pooling even the smaller objects, they could probably benefit you. See if JVM pauses are a pain for you. Now with the successes, some myths broken, we went over the network. We were able to go off box even for low latency caches. We were able to parallelize our workflows because now we were more on the network. We were able to reduce the CPU load on the hosts. We learned that caches are pretty stable. These could be wonderful solutions for high scale systems. A tip that you could use in case your requirements are that you want more consistency over latencies, then as you read from these multiple replicas, you could establish a quorum there and then itself, which would take a little more time, but much lesser than having to go to a data store or database. And that could also just fasten up for your business needs. The win was that we are now, my largest of the caches is serving somewhere about 500 million keys per second. It stores about 250 gigs of data. And the network that is consumed over these caches is somewhere about 2.5 terabits per second. The parallelization, the replication, and the sharding enabled all of this. Right from the press, there is a request coming to us on which we will be onboarding and supporting a cache for 4.5 terabits per second with 7.2 terabytes of data to be cached. And it was passable. This is where we were more like, you can do it. There are not problems which will not be solvable. You can do it. Go on for it. Okay, let's touch back on the transparency problem that we were talking about. All of this was done, things were over the network, but the systems were still opaque. We were not logging much. We built this ad eventing system. Real-time introspection and debugging has its powers. Once you know what is going on in the system, you will be able to innovate upon it. You will be able to analyze. You will be able to figure out where you can optimize your systems. Also, the machine learning systems would love this. They would be able to get more and more of this data to build better scores for, in our case, ad serving, conversion scores, click-through rate scores, and relevance scores, which further improve our business. The challenge was that there will be hundreds of millions of ads, and we estimated that the data will be generated at about 4 terabytes per second. At this scale, even serialization was challenging. The CPU was clogging to just serialize so much of data. Writing to a file was completely off the table. We took some time. We were naive. We started simple. We loved the complexities. We thought that we could dump all the data on an SNS topic, pick it up from the other side, and everything will work fine. There were thousands of ads in every request. 256 kilobyte payload cap of SNS would not work here. Okay, we can change it to Kinesis. Kinesis has a payload size of 1 megabytes. That should be fine. Well, it was fine for some of our use cases, for some of the requests where the ads were really at thousands or 2,000 ads per request. But at P100s, these were at about 20,000 ads in one request. That was again over the 1 megabyte limit. Also, Kinesis started to throttle us because when you throw these big payloads to Kinesis, the hot shards happen and Kinesis would throttle you. Okay, we broke the payload down, and each ad or each request started to break it into multiple chunks. We would shove that onto the Kinesis stream, and then later pick it up from Kinesis data streams, attach it to an EMR cluster, and then join the data and make it available. To get the data into S3, we attach the Kinesis data stream into Kinesis Firehose, and Kinesis Firehose would put our data into S3. When we tested, we were able to log 120 terabytes per hour. This had somewhere about 2,500 shards, Kinesis shards running, but it was egregiously expensive. It's like millions of dollars per month. It's like, no. Is it really worth it? Let's go back and look up our requirements. Even if we were able to generate this much data, we are just logging it. Somebody would be consuming it. They would need to process it. How would they even process it? There is something missing out there. we realized that we did not need 100% of the data to be logged. The other realization was that we may not need it to be logged within seconds. Tens of seconds should be fine. This is data analytics going on or machine learning going on. This is not real-time request response. Again, the Eureka moment kicked in. We simply cut off the middleman. We were batching already in our ad servers. We started logging that batch directly to S3. We saved 98% of our costs. Now the solution was somewhat seemingly okay for the business growth as well. The end-to-end latencies also did not go bad because, again, at this scale, the buffer was filled up very fast and we were able to shove it off. The data was available in S3 in about 3 to 5 seconds. You can tune the amount of data that you want to batch, so that could vary your latencies on how you get the data into S3. And the end-to-end latencies after the whole of the data analytics and machine learning processes was now about 10 minutes. The data was available for them to do the next jobs that they would have to do. On the other side, we also reduced the amount of data that was to be logged in. We started logging much lesser for what was relevant to be logged. And different teams came about and said, hey, we want to know why an ad got dropped. Somebody said, we wanted to know what are the general scores generated. For somebody, they said that we want to know where is this ad sourced from. We logged only those specific details to those teams and gave them their data out there. With this, we reduced the total amount of logging to about 1.2 terabytes per hour, and that was somewhat manageable. The costs were too less. The business was benefiting by all of this, and we were able to launch a successful ad events system. Now, with more and more data generated, the hunger continued to grow. Many teams also copied the solution and started to generate more and more data. We needed a centralized data lake in which we can aggregate all of this data, keep it together, and then use it for a variety of use cases. Let's go deeper into our data lake creation now. The first system just centralized the ton of data that we had. It would poll daily into RDSs, take a daily dump of it. It could poll into or hook up into S3 dumps that other teams were creating. All of the data was cataloged into Glue, and then EMR was processing all of this data. We opened up the user interfaces over Redshift and Athena, and that's how the developers would be able to query it, run analysis on it, and so on. There were wins, not to deny, that the system was able to run the jobs in about 4 to 6 hours. There were petabytes of data available. It was just working fine. But there were challenges. There was always need for more data. The reaction time was to be reduced for customer behavior responses. If there is a shopper who's coming in to do something right now, and if they've done some events, that data should come back and feed back into the machine learning systems more or less immediately. We can't wait for 4 to 6 hours for that to happen. The developer productivity was getting impacted because over Redshift and Athena, every query used to take about 10 to 15 minutes. Now, developers don't write the query first time in perfectly. So the time was not to exactly execute that query. It was time to build that query after several attempts, and each attempt was taking those 10 to 15 minutes. So that was something that we could improve. And lastly, we had an online-offline skew. What this means is that the data that was available to the ad server in real-time streams, whereas the data that was available for these analytical systems was a daily dump. There was a difference. Like, there was 10 versions of the data in the online system, and there was only one version getting to our analytical systems. That tipped off a bunch of analytics. That tipped off a bunch of machine learning systems itself. Those had to be solved. With more and more teams wanting to provide their data into S3, it was just time when S3 started to throttle us. The writes went up higher and higher, and S3 capped us at 3,500 writes per second. With more complicated jobs running, S3 capped us on the reads for 5,500 reads per second, if I remember correctly. The solution was that we randomly prefixed a prefix to the S3 buckets and started writing to 16 to the power 4 buckets out there. Since all the data was still cataloged into Glue, there was no performance degradation for this. But again, it was time. Glue started to slow down then. There was more and more data. There were larger chunks to be read through in those batch jobs. More and more S3 buckets were to be pulled in for job processing, and Glue started to slow us down. What we realized was the need for a searching system is there. Glue is basically supporting EMR by figuring out what are the right S3 buckets that need to be pulled up and given to EMR for the further map reduce jobs that would run there. We built a search solution for there. So we had an orchestrating system created, which would listen to the jobs that were fired on EMR. It would then go search in the Elasticsearch and the Glue catalog to figure out what are the S3 files to be picked up, what are the S3 buckets to be picked up. It would go pick those specific ones. And this improved our bottleneck on Glue. It also improved our overall delays in the job processing manifolds. Now, there were problems in the overall 4 to 6 hours of job that was still taking in. This infests in two forms. One is from the data ingestion side itself. If the data is being generated as a daily dump, of course, at least a day will be needed to get the data, and only after that something else can be executed. We augmented our ingestion mechanisms to get to also allow ingestions using Kinesis, Kafka's SNS SQS. The other part of this slowness was coming from the EMR jobs that were slowing things down. There, we augmented our EMR with Apache Spark, and that again reduced the load times. It was able to parallelize the workflows much more efficiently, and we were able to build stuff. Realize that the delay was also because the whole system was architected as batch jobs. Now that the ingestion was fast, you could run a job as soon as the data is available out there. But this job will process the data and make it ready for the next job. Then that guy will process the job, transform it, join it, do whatever, and then make it available for the next job, and then the next, and then the next. So if there are 4 or 5 iterations like this, there is still a delay. Using Kinesis and Kafka, what we were able to get to was that real-time joins and analytics were possible. It is a little bit expensive, but depending on your use cases, you can figure out which ones do you want to pay for. To improve the developer productivity part of it, we also indexed some of the data into Apache Druid and Apache Superset, which was nearly able to get real-time responses to the developers. Once the queries were fastened up and they wanted to query the whole set of the data, they could now fire that same query on Redshift and Athena and get their results faster. With the successes coming here, we now had petabytes of data available. We could offer about 15 minutes of overall end-to-end data ingestion latencies. The real-time joins and analytics was possible with Kinesis and Kafka. Of course, they were a little bit costly, repeating that. To reduce our costs, we employed S3 tiered storage. So the data that was not being used or the data that got old, those were put into colder S3 solutions, which were much cheaper. Another optimization was that we reused our EMR clusters. EMR charges you even at the boot time, and by reusing them, we reduced the boot times multiple times spinning up the EMR cluster, and that also improved our costs tremendously. All this data proved gems and jewels to our machine learning systems. Our analytics improved, and it was fun. Just to reiterate before I hand over to Kun, some of the salient points that we learned through our journey. Focus on not letting your system be boxed in a box. Continue to scale horizontally. The world is there to solve some problems for us. We don't need to solve our problems. Pick up the latest solutions, keep yourself abreast with the latest technologies going out there. Don't be naive to love the complexity. It's a common trait that engineers would want to solve big problems, but try to solve problems which actually get your business benefits, your solutions out there. And lastly, having a good system is much better than not having a perfect system. Thank you so much.